In Chapter 7, we're going to focus on using the integral and the antiderivative to find both area and volume. So we'll be working in two-dimensional and three-dimensional space. In Section 7.2, we'll focus just on finding area in the plane. We'll look at area as an accumulation of Riemann sums. So the limit of the summation as the number of Riemann sums approaches infinity. We'll see how you find area between two curves, and then also finding area with respect to y in our integration terms rather than with respect to x. You've got a couple ways that we've already talked about how to find the area under a curve but above the x-axis. And we used estimating in terms of RAM and trap and simp. Those all give us estimations of varying degrees, either an overestimate or an underestimate, depending on the concavity of the region that we're finding the area of, and depending on the type. If it was a trap and one kind of concavity, that means one thing, but a simp with a different kind of concavity means something else, or a RAM. We can only find an exact area using an integral, and the integral is usually done with respect to x. If we want to go beyond the x-axis, if we don't just want to use the x-axis as a boundary, we'd rather use another curve as the boundary line, then we're going to use subtraction. So we find the common bounds that are had by the region, by both the upper and the lower curve. We establish an upper curve, which we call f of x, and f of x needs to always be above the g of x function. We establish a lower curve, so that would be the one that's always has y values lower. And we subtract the difference between the two. And that would essentially find us the area both above and below, so nested between those two curves. So if we want to find the area of a region between cosine and sine from 0 to pi thirds. So I find it always really helpful to have a visual. And so we know that cosine intersects at pi over 2. And then sine coming up through the origin. And sine intersects at pi. And we're going from 0 to pi thirds. So pi thirds is about right here. And we want the area between the two curves. So we're looking at this area here. So we'll set up an integral. The bounds will go from 0 to the intersection point of pi thirds. The upper curve, upper boundary, is formed by cosine of x. The lower boundary formed by the sine of x with respect to x. So we'll have the sine of x plus the cosine of x plus c evaluated on 0 to pi thirds. So that'll give us the sine of pi thirds plus the cosine of pi thirds minus the sine of 0 minus the cosine of 0. So we're looking at square root 3 over 2 plus half minus 1. That would give us the exact area between those two curves on that interval. All right, let's think about a parabola and a line intersecting. So we're thinking about the parabola that's dropped down 1 on the y-axis. And then we're thinking about the line with a y-intercept of 1 and a slope of 1. And so we want to find the area bounded between these two. So we'll also need to find the intersection points of these two. So we're going to set these two functions equal to each other. And we'll solve for where they intersect. All right, this function factors nicely. x minus 2 and x plus 1. So x is negative 1 and x is 2. So those are our boundary points. And so we've got the area going from negative 1 to 2. Our upper bound is formed by the line x plus 1 minus our lower bound, so that would be x squared plus 1 dx. So we'll go for the antiderivative of that. Negative 1/3 x cubed plus 1/2 x squared plus 2x plus the constant c on bounds negative 1 to 2. So that'll be negative 8/3 plus 2 plus 4 minus, let's see, negative minus 1/3 minus 1/2 plus 2. So that looks like it'll be 8 if I add up 2, 4, and 2, and then minus 3. That's if I do negative 8/3 minus 1/3, and then minus half. So I'm looking at 4.5. All right, when we use our calculators, it's required that we set up a full integral to show the equation, but then we can use Math 9 to evaluate the integral. So again, we've got a good visual, should have a good visual of what an exponential to the negative x looks like. So there's our y equals e to the negative x. And then we have cosine, which also starts at, we know that this is 1, so it starts at 1. And we're going up to 2 pi, which is the return to the peak of the curve. And we want the area between. So I've got a bunch of area between right here. They switch, and I've got area between, and I might have a little bit of area in there depending on how accurate I drew my graph. So I'm going to need to take a look at this to find the intersection points. When I take a look at this on my graphing calculator, I do confirm that there is area here that I need to find. So I use my second trace to calculate the intersection. And so this first intersection point happens at 1.2926957. Now make sure that you store that in your calculator. Don't just round. If you round, you're going to lose accuracy. And so you want to store that as alpha A in your graphing calculator. We'll look for the second intersection point. That would happen closer towards the end of 2 pi. So I'm doing that right now. And this intersection point turns out to be 4.7212928, and I'm going to store that in alpha B. Again, store rather than round. If you don't remember how to store, you've got to quit from the function into a home screen. The store button is right above on. You pick store and then hit an alpha key and then pick the corresponding letter that you want to store it into. Okay, now we're ready to set up our integrals. We're going to let the calculator evaluate the integrals, but it's our job to set them up. So I'm going to have an integral that starts at 0 and ends at alpha A. And as long as I've labeled A somewhere on my my work, then I can just use A in my equation. And in that region, the cosine is the higher function, and e to the negative x is the lower function. So I use parentheses to properly set that up, with the cosine being the higher function. I set up a second integral that's going to go from a to b. And in this integral, the e to the negative x is the higher function and cosine is the lower. And my third integral will go from b to the end of the interval, which is 2 pi. And in that interval, cosine is back to being the upper function, and e to the negative x is the lower function. All right, so again, the calculator will evaluate that using the alphas that you've stored. Your job is to write it down correctly. Now you can either evaluate each integral individually and then keep track, or you can do it all at one time. If you decide to do it individually, this first integral is 0.2361083419. Okay, if you're going to do it individually, you have to take all the decimal values. If you just do it all at one time on the calculator will remember all those values for you. The second amount of area is 2.227165043. And the last interval is 0.9929241435. For an overall total of 3.45619758. Okay, you only have to show me in your final work, okay, rounding to the thousandth, so checking what happens after that. So, you know, your final answer would be 3.456. Now we can also integrate with respect to y, and your calculator can do that in Math 9. You just use alpha y's for your expressions. This really works well with functions that have y-intersection points or do not pass the vertical line test. So these curves fail the vertical line test, and so it just is easier to work in terms of y. So you're going to be working maybe with a cubic function, a squared function, but in terms of y that fails the VLT. So if you were thinking visually of what this looks like, okay, this is a parabola that's been moved one to the left, and it's got an upper and lower branch. Okay, this is the equation x equals y squared minus 1, or it's y equals plus or minus the square root of x plus 1. So it's both, but it fails the vertical line test. And then we've got the line y equals x plus 1. So you've got intersecting the y-intercept of 1, and we're looking for the area bounded between them. Now you could set up this integral really either way between the two. You could set it up in x terms or y terms. For our purposes, we're going to set it up in y terms. And then you'll be subtracting, starting with the right-hand function minus the left-hand function, as opposed to the upper minus the lower. Did we talk about that up here? Yeah, so you want the function on the right minus the function on the left. So this would be right minus left, as opposed to the top minus the bottom. So the integral in y terms, using our y boundaries, the y boundaries are from 0 to 1. The right-hand function is the line, and in y terms, that line is y minus 1. And then minus the parabolic function in y terms, so that would be y squared plus 1 dy, or in simpler terms, negative y squared plus y dy. So then you can do that by hand, or if it got more complicated, you could do it with alpha. You could do Math 9 and use all y's, and it would work fine. This one also could have been done in x, So in x terms, the boundary would have been from -1 to 0 if we were looking at the x values. And then the upper function would have been the square root of x plus 1 minus the lower function of x plus 1. So either you're integrating in y terms, which I think is going to be an easier integral, or you're integrating in x terms, which is going to require you to integrate a square root. So I think probably easier by hand to do it in y terms as opposed to x terms, but you'll get the same answer either way. All right, so that is just a quick review of area that we did last. We saw this topic last year, and so this is not new, but it also was not, oh no, this part actually was the last part that was on your AP exam. It was the volume that wasn't on your AP exam. So let me just sign off for now, and I will see some of you in cohort tomorrow.